Good morning. Good morning, everybody. I'm Bettina Berger. I'm from the Australian Plant Phenomics Network at the University of Adelaide, and it's my pleasure to chair this first session on biotic and abiotic stress responses and some of the phenotyping technologies that exist to investigate those traits. And it's my pleasure to introduce our first keynote speaker for the IPPS8, Katie Gold from Cornell University, who will be presenting on plant disease sensing and how to use that information for management intervention. Thank you very much, Katie. We look forward to your talk.
Hi. Okay. So I either tend to wander or cling to the podium for dear life. So we'll see what we do this morning. Okay. Thank you for the introduction. It's really great to be here. I don't normally think about the work that I do. Is this feedback? Okay. As phenotyping, but this is making me consider otherwise. So the title of my talk today is Plant Disease Sensing for Management Intervention. I'm an assistant professor of Grape Pathology, but my training has been pretty interdisciplinary. I was co-advised by a remote sensing scientist and a card-carrying plant pathologist, and spent some time at the Jet Propulsion Lab working with NASA on their forthcoming sensors before joining Cornell, where I was told, take all that stuff and find the disease. It's harder than it sounds. And this is because disease is the result of really complex interactions between antagonistic organisms and their environment. These interactions are very dynamic, both on the individual scale as well as an aggregate. For example, this is the concept of the disease triangle, and this is the fundamental theory of plant pathology, which is that you only get disease when you have a virulent pathogen interacting with a susceptible host within a conducive environment. And only then do you have the product of disease. Otherwise, you just simply have the components. And you'll hear me refer to this as a pathosystem, especially because with sensing, you're not detecting just the individual pathogen. You're not detecting the susceptible host or the conducive environment. You're detecting the intersection or the union of all three of these things, which we call a pathosystem. And sensing is a really amazing tool for detecting disease, because it's really the only scalable detection method we have in our disease control toolbox that can transcend historical limitations to facilitate actionable early warning. Plant disease results in over 8 billion pounds of pesticides used annually. And while pesticides are critical for modern agricultural production, it's undeniable that their overuse has environmental, financial, as well as pathogen resistance consequences. And sensing is really the only scalable tool that we have that can address these challenges at the global scale at which agriculture is conducted. Remote sensing has the ability to transcend historical boundaries. My lab has pioneered an integrated approach to plant disease sensing that's anchored within the concept of the plant disease triangle, but takes into account the management dynamic, the fact that agroecosystems are defined by human interactions, and that plant disease sensing is the combination of sensing all these different aspects. My lab is the Grape Sensing Pathology and Extension Lab at Cornell Agritech. We were launched on February 1st, 2020, so quite an uneventful time if anyone happens to remember. We specialize in a wide range of technologies across scales. Our bread and butter is hyperspectral imaging spectroscopy. I work quite closely with NASA and the Pest and Disease Risk Mitigation Lead for their agricultural consortium, NASA ACRES. And we work with their Cadillac sensor, AVIRIS. We're now up to AVIRIS-3. But we use multimodal and multi-scale technologies, everything ranging from drones, in-field robotics, as well as in-lab sensors. And we, with our overarching goal of looking towards management intervention and real field usage. So in thinking about what did I want the audience to come away with, I was thinking about some of the luxuries that we have when you're working towards a breeding program, perhaps a phenomics environment, that you may not consider if you were to think about how these technologies might be used in a commercial sense. For example, a production environment can be optimized for sensing if you're working in a controlled environment or with a breeding program in the field. For example, we can, in viticulture, we have different practices we can do that can optimize how much of the cluster or the foliage is available simply to make it easier for the camera to sense things, or we can put up QR codes. We don't have that luxury in commercial production. Additionally, confounding factors. We don't have the ability to control for confounding factors such as co-occurring abiotic or biotic stresses in commercial operations. We need to be able to detect disease in light of all the other myriad things that could be going wrong, which could range from anything from, a co-occurring biotic stress to, the vineyard manager's kid drove a cart into the trellis post. These things all cause stress. Additionally, the timeliness is a very important concern when you're looking towards a commercial operation, in that this information needs to be acquired ASAP and it needs to be delivered to the decision maker ASAP. Whereas when you're working with a breeding program or perhaps a more controlled environment for phenomics, you do have some timeliness. For example, you want the data to be delivered in time for the graduate student to graduate on time, but not necessarily within 24 hours. Additionally, breeding programs have the ability to adopt technology quickly, within a season to season or even within a season, where commercial operations are quite slow. And finally, the overall goal of phenomics and sensing in a breeding program environment would be disease quantification. And that's not exactly the goal when you're sensing disease in a real commercial operation, whereas your goal is to trigger a management intervention, not necessarily say exactly how much disease is there. And this does change the way you should conceptualize your sensing system as well as deploy it. So before I go any further, though, I do want to establish what is a management intervention. A management intervention is, at its most simple, is an action that is taken in time to affect the outcome. This could be something as like a fungicide application with something with kickback action to stop infection in its tract. It could be plant removal or cultural control that could modify the environment to try to make it less conducive for disease to develop any further. And some of the desirable outcomes that we hope this intervention will help us achieve have a wide range. They can be from quality preservation to yield preservation. In grapevine, which is where I work, yield is not king as it is here with corn in Nebraska. Quality is just as important, if not more important than yield. They can also be the desirable outcomes could be more centered around the pathogen disease itself. For example, we want to reduce the amount of inoculum, not necessarily stop its spread entirely, just kind of keep it to a dull roar and keep that spread rate low. So if these are the different sorts of actions someone could potentially take, we do want to add a layer to that, though. We want this management intervention to be effective. So if we add that qualifier to the statement, this means that an effective management intervention is one that is done in time to change plant health outcomes for the better. And management interventions universally are most effective when the time between disease onset and that management intervention is short. Now, this is in contrast to preventative management, which seeks to delay disease onset indefinitely, ideally, but just delay as far as possible. Whereas a management intervention is something that occurs after disease has already started. So this T-responsive, effective management intervention depends on this interval being as close to zero as possible. Plant disease sensing can improve plant health outcomes by adding this element of detection that breaks apart this T-responsive into two different phases, the time between onset and detection and the time between detection and final intervention. Adding this element helps increase stakeholder knowledge, as well as minimizes their uncertainty during this key decision-making window and give them two sorts of phases. So if you want to design a sensing system with this in mind, there are two very important things you must keep central within your conceptualization, as well as if you're looking for translational uses for a system that already exists. And first and foremost, you must consider the pathosystem biology or disease physiology, how the disease manifests and what are the conditions that favor it, because this determines how you should be optimizing your sensing resolutions and when within this T-responsive phase should you be seeking to minimize decision-maker uncertainty. I'm going to go through two examples that kind of explain this philosophy that we have. So the latent phase of a pathosystem, the time between infection starting and symptoms becoming visible, and its native disease physiology. This is key for determining how you should be optimizing your spatial, temporal, and spectral resolutions, whereas the action threshold is what determines when you should be seeking to apply or deploy your sensing system within this window. So what are the 3 different sensing resolutions? I'm sure this is not new to you all, but bear with me, I'll go through it. Every sort of sensor, regardless of whether it's hyperspectral, multispectral, has a spatial, a temporal, and a spectral resolution. Your spatial resolution is asking, what is your pixel size? Your temporal asks, what is the revisit time? And the spectral is what light and at what sorts of intervals is it being measured. The length of the latent phase and the disease physiology informs how you want to optimize these 3 resolutions, because we unfortunately don't live in a perfect world. We don't get to pick the perfect spatial resolution, the perfect temporal resolution, and spectral resolution, either because we're limited by physics or we're limited by budget. For example, you might not actually want or need, depending on your latent period, the resolution of a single plant, or you might need multiple pixels per plant. If you have too fine a spatial resolution, though, this impacts your signal to noise ratio. So more is not necessarily better in terms of making your data useful. So it's not just a more better for each of these sorts of resolutions. There are trade-offs that you want to make. And which one of these things is most important depends on how long your disease or pathogen, how much time you have before it begins to sporulate or spread to other plants. If you have a long time, well, here, I'm getting ahead of myself. The next one I wanted to talk about is the action threshold. So this is how the stakeholder is thinking about this disease and how it impacts the context of their whole season management program. And this tells you whether you should be prioritizing minimizing the time between onset and detection or detection and intervention. For example, we have quarantine diseases. Think of the early stages of the COVID pandemic, or, with Ebola, Marburg virus. These are the sorts of diseases that have a 0 tolerance threshold. If it's there, we're killing it, we're getting out, we're acting immediately. Versus disease that are managed much more similarly to the common flu. We expect it to occur annually. We take actions to try to minimize it, but we're not trying to fully exclude it, and we expect that it will occur every year, and we're just trying to keep it down to a dull roar. Depending on which sort of management threshold you have, will tell you how the information you could provide would be most useful to your stakeholders. So I'll walk you through this for a moment. Oops, sorry, that didn't work out. With 2 diseases that are plague my vineyards as an example for you for these things. This is grapevine leaf roll virus. I'll call it GLRV, or just leaf roll disease. This is a viral disease, so we call it like a systemic disorder. There's no cure for a virus once a plant has one. There's no sorts of vaccines, and you don't recover from it like a human can from a virus. So the only cure for a viral infection is removal. And while it does not kill the plant outright and immediately, it impacts the quality, which is very important in grapevine production. It makes quality more variable, and it also decreases vine lifespan over time. And it has, and more importantly, it has a year-long latent period. In this latent period, the plant is infected and infectious, but it does not manifest visible foliar symptoms, which you can scout for to detect it. It is causing a negative impact to the plant. It's disrupting the quality of the berries being produced, as well as reducing its winter survivability, but it's not yet causing this leaf reddening that you can address and say, oh, this one is infected. Additionally, too, only red grape varieties will ever bother to show red leaves for you to scout with. White grape varieties do not show that. They just decline in vigor over time. You get less yield, you get worse quality, and that during that time span, these are all infectious, so they're serving as reservoirs and inoculating their peers. So given this long 12-month latent phase, this means that your detection needs really high spectral and spatial resolution. You want to be detecting it during this latent phase. You have a long window to do so. If you can detect it asymptomatically anytime during that 12-month period, you're going to be providing your stakeholder with important information. Additionally, you want high spatial resolution because you want to detect it on an individual plant level. And you can also, given these pathosystem realities, you can tolerate lesser temporal resolution because you have that whole year in which you can still make that your information will still be quite useful because it's going to be asymptomatic for that whole year. The urgency is not there. Now, the fact that it has a 0 tolerance management threshold means that the decision makers are going to benefit the most from improved information between onset and detection, the first half of that T responsive. because we cannot tolerate, there's no cure, there's no action you can take other than killing the plant. And the longer you leave the plant there, the more likely it is to serve as an inoculum reservoir for others and spread the disease. You want to give them that information as quickly as possible to minimize that T onset to detection. So in order to address this disease, we crafted a project in hand with the Jet Propulsion Lab to use their airborne imaging spectrometer, AVIRIS-NG, to detect grapevine leaf roll virus during the asymptomatic phase. And this project was spearheaded by my graduate student, Fernando Romero Galvan, who is set to graduate and is on the job market, if anyone is interested in this work. So with this, we made the first report of asymptomatic viral disease detection at the airborne scale. And this is notable as successes we've seen at the airborne scale will often transfer to the spaceborne scale. And as NASA is looking to launch a new hyperspectral satellite by the end of the decade, this makes us hopeful for our ability to use this forthcoming satellite to do regional assessments. We found that airborne spectroscopic imagery could correctly classify non-infected symptomatic and asymptomatic grapevines with 81 to 87% accuracy, and that the spatial resolution that was most optimal for that signal-to-noise ratio was actually 3-meter resolution, which was upscaled from the native 1-meter resolution. So now, in contrast to this work, though, I'd like to introduce you to grapevine downy mildew. This is an omycete, and it has a rapid polycyclic disease cycle. It's the opposite of grapevine leaf roll in that it can change very, very quickly. So timeliness is of the utmost concern. It is quote unquote controlled with fungicides on 10-day intervals. However, we are facing an uphill battle against fungicide resistance as well as with EPA restrictions on broad spectrum fungicide uses. The more we can control the disease, the better, because we're simply losing our chemical control options that we've historically relied upon. And it's the number one limiting factor to grape production in humid climates. Now, this short latent phase, within 24 to 48 hours, you're going to go from infection to visible symptom. This means that change detection with high temporal and spatial resolution will be the most helpful for a stakeholder. And even if it means that you have to forego your spectral resolution, because you don't need that high spectral density, that wide spectral range to detect it in that asymptomatic period, because it's going to become symptomatic so quickly. And simply getting them that information quickly will have the best outcomes. Additionally, because it has a non-zero tolerance threshold, we expect to have this every season. This means that decision makers will benefit from reduced uncertainty between detection and intervention. They know they're going to get it, but they don't know when or exactly where it's going to start. So if we can minimize that time between the disease starting and the time they make the intervention, the better. So for this project, we've been exploring spaceborne and aerial UA multispectral sensing with my graduate student, Kaitlin, looking to move past detection and into surveillance. So we've been working with commercial Earth observations from a provider called Planet Labs, which launches CubeSats. So we've been working with multispectral satellite imagery at both the 50 centimeter and 3-meter resolution to see if we can do change detection for downy mildew. And while we found that, yes, we can detect disease, we can really only detect it at the severe levels, which is that's kind of past the economic injury threshold. But most challenging is that the nature of the CubeSats is that the exact CubeSat that you're getting sensing your system every time is not exactly the same one. And their pipelines were not quite ready for us to make models that were very robust to those differences in hardware across time. So while we did find that fundamentally it worked and we could detect it with 85% accuracy, we wanted to do something that was more reliable for surveillance and moving simply from detection to a more of a passive operational mode. So, but the problem with moving this along towards and trying to push these technologies out of the technology valley of death and in towards application is that vineyards are beautiful, but they are challenging to remotely sense if that's your only technology. As you can see here, the foliage is predominantly on the side canopy. And most diseases, regardless of whether they're viral diseases or fungal or mycete diseases, develop first in the lower inner canopy, which is not going to be visible or directly visible to a sensor. And this is a huge barrier if you're not working with a hyperspectral sensor. Now, hyperspectral gives you the ability to see the chemical changes induced by disease throughout the plant. But as we've kind of gone over here, not every disease is going to really benefit the most from having hyperspectral. You're going to want change detection. So some of these problems with the confounding foliage that we see is that it leads to these misclassifications. For example, down in this top part, this is our misclassifications from our leaf roll project out in California. By not accounting for co-occurring abiotic stresses, as well as this kind of inner canopy condition, we had numerous misclassifications, which we also saw in our grapevine downy mildew project. However, that misclassification came from co-occurring biotic stresses. And there was kind of simply a barrier we just couldn't break through with remote sensing alone, which is why we began pursuing proximal sensing in order to complement our remote sensing to inform and trigger a management intervention. So this is the beginning of a research partnership with Yu Jiang, who is an engineer who was hired within a month of me at Cornell Agritech. Dr. Jiang's lab specializes in applied field robotics and AI. And, as I mentioned, we started in 2020. So a little bit of trauma bonding there, exactly, starting these new faculty jobs and, having the world simply fall apart. So during this time, we started having Zoom coffees every day just to stay sane because we had no friends, we had no lab members, and nothing else to do. And we came up with this idea of integrating his robotics with my remote sensing to have a fully integrated and holistic disease detection system. And this project has since received funding from NASA, from NIFA, as well as numerous other sources, and has turned into a really wonderful friendship. So we conceptualized this idea of a multimodal and multi-scale disease sensing system where the remote sensing could be used for regional scale assessments that could trigger both UAV and ground-based sensing for more high-frequency scouting to address diseases that have high change rates, using robotics for model training and validation, as well as in-lab-based hyperspectral sensing to improve our biological understanding of why we're able to use sensing in the first place for disease detection. And importantly, this has become kind of the central theorem of which we've structured our labs and our collaboration around, is providing interdisciplinary opportunities for our students. I'd like to highlight Ertai Liu, who is Yu's student, who's the architect for the robot I'm about to tell you guys about, and my student Kaitlin Canali, who the two of them have partnered together very closely, and it's led to much more richer dissertations, richer training experiences for the two of them than they would have gotten otherwise had they been siloed in engineering and plant pathology. So these diseases, again, common vineyard diseases, unhelpfully co-occur and manifest first in the inner and lower canopy. However, what we do have going for us if we want to address this problem with our holistic system is that they have contrasting disease physiology. So returning to that concept from the very beginning, one of these is a virus. It's going to have a systemic disorder. It's going to be very chaotic to plant chemistry, whereas the other is a foliar necrotic disease. It's going to cause necrosis on the foliage, which is going to look very different from the impact that a systemic disruptor will have. So if we can yield side canopy imagery that can sense these two differences, we'll be able to generate much more high quality ground validation data to train our remote sensing with at a scale that's simply infeasible to achieve otherwise. So this is our closed loop sensing project where we conceptualize that the robot provides improved ground validation to both UAV and airborne and spaceborne remote sensing. And then in turn, the remote sensing provides strategic deployment of the robot to areas of the greatest uncertainty where models need improvement, or the areas where the disease appears to be the most likely to provide confirmation. So for this project, we started to do working with the UAV for downy mildew for the rapid change detection to supplement scouting, and working again with AVIRIS-NG to develop regional monitoring and assessments for high accuracy detection during that asymptomatic phase. But first, I'd like to introduce you to the PhytoPatholobot, which is a dissertation, Ertai Liu's dissertation project. And if you're going to ask me questions about this, I urge you to remember that I am the plant pathologist in this collaboration, not the engineer. So the PhytoPatholobot has a ClearPath Husky robot base, and it has RTK GPS navigation and a strobe light enhanced RGB camera, though it's been recently updated to have a 10-band multispectral camera. And this is it rolling through the pathology vineyards at Cornell. And it navigates through these vineyards as you and I do. It uses its eyes to visually navigate through. And this is a major advance over GPS-based. It only needs a few georeference points, and it's able to completely traverse the vineyard on its own. And the main advantage of this is that its navigation does not require any human annotation to train. It can simply look at where it's going and figure out how to get there. Not without some flaws, of course. For example, one time the robot almost ran me over. I didn't appreciate that. However, it has only improved in time, and its ability to navigate the vineyard on its own allows us to focus on the most important part of the robot from my perspective, which is what its camera is seeing when it's looking at the side canopy. So Leo has built this really phenomenal platform that's since been updated as well. However, it's a multi-stage feed-through maps that automatically combine and then unify the convolutions and the transposed convolutions. Once again, remember, I'm the plant pathologist. And the takeaway here is that the result of the computer vision system here is that we can effectively do this in near real time so that we can immediately generate the maps and provide them to a stakeholder or to a researcher to make a decision. And this is an example of what its imagery looks like. I'd like to acknowledge the MVP here, my vineyard manager, Dave Combs, who has spent countless hours training the early versions of the robot's computer vision to be able to detect the disease. He's been working in vineyards for 25 years, and now our robot is just as good as he is at identifying disease in its imagery. So Dave in the vineyard interacting with the vines is still better than the robot, but that margin is getting smaller and smaller every year. And it's now just as good as he is in looking at its imagery, which is really, what more could you ask? So it's able to predict downy mildew with an R-squared of 82, and it has a very high accuracy rate for detecting reddening caused by grapevine leaf roll virus. And it's now able to do this, at the same time. They were trained separately and then worked together. And this is an example of what the maps look like. So on the top is the robot maps, and then the bottom is the ones generated by the students. The way that humans scout the vineyard is they go on a panel-by-panel basis, and a panel is about 3 to 4 grapevine, and just the nature of how they grow is you can't really divide them out by plant, whereas the robot's able to make a classification for every frame within its vision. So you get a much finer and detailed training product to use with remote sensing imagery. So after training the robot, the next stage was to conduct campaigns to use this imagery to train the remote sensing and compare it to the human training process, the human validation. So our first campaign took place over the course of 3 years at the Cornell Pathology Vineyards in Geneva, New York. These are the hub for our applied grape disease management profile. So we have about 8 acres of vineyards that have a very nice and convenient artificial disease gradient, which is excellent for building and training models on. And we also know exactly where disease is going to be and can estimate exactly where we're going to get the most severe, given that the different fungicides programs result in different disease. So we did a comparison of 3 different modalities of disease detection. They have a couple similarities and differences. For example, the students, the phytopatholobot and the UAV all have autonomous navigation, while the students and the robot both have that side canopy view. And they share the RGB-based sensing. However, the student's modality is optical, biological. Okay, I'm gonna stop with that joke. But the real difference between them all, aside from the fact that one are graduate students, the others are robots, is that it takes the students about 5 hours for a team of 6 to scout every single vine within 1 acre. In contrast, the robot can do 1 acre in 5 hours, and the UAV can do 1 acre in 5 minutes. So there's a major time improvement there. Additionally, the workflows for the ground robot, and the UAV are reproducible, and we can go back to that imagery over time to fact check what we saw. It's not ephemeral as a human disease rating is. We find that both the humans and the robot provide comparable ground validation for multispectral UAV-based sensing when visible symptoms are above 10%. So actually these numbers on the figures here have actually since been updated as we added more training data, which is that both the robot and the humans effectively can train models that are about similar in terms of accuracy in detecting side canopy downy mildew, can train UAV-based models with about similar accuracy, just under 80%. But this is only when the symptoms surpass 10%. And this is unfortunately above the economic injury threshold. So that's something we're working on in the next phase of this project. Additionally, we had the opportunity to participate in an AVIRIS campaign in Southern California. So AVIRIS is really the Cadillac of imaging spectrometers, and it's owned by NASA and the Jet Propulsion Lab, which means that it's very difficult to tell it where to go. So when it's going somewhere that happens to overlap with your biological system of study, you do your best to follow it. So we sent 3 graduate students and 1 robot 3,000 miles away for a 10-day field campaign in order to collect the robot imagery along with the hyperspectral imagery collected by AVIRIS. And this campaign was really successful, and it was a wonderful learning opportunity for our students. And they all came back in one piece, thank God. And we found that the robots and the humans, once again, yielded comparable model accuracy. And the robot actually slightly outperformed the students in terms of training for leaf roll disease detection. And what we actually found that was very interesting was that training AVIRIS imagery with the robot data imparted less confusion to the model, less variance to the model due to variance in soil, shadow, and vegetative abundance. When we looked at the sources of misclassification and whether they were correlated with soil abundance, shadow abundance, and lack of vegetation, we find that the humans were more likely to be confused by these things than the robots were. So the robot was a little more resilient to disturbances from there. So it doesn't mean that their robot is a better scout than the humans. It means that the robot was a slightly better trainer for the remote sensing data. And excitingly, too, when we looked at both the relationship between the UAV and the AVIRIS-NG, which differ in terms of their resolution, multispectral 10-band versus hyperspectral 400 bands, we find that both the humans and the robots, the models tend to pick up on similar spectral features, though there is some difference between them. For example, over on the left, the robot is the blue and the human is the yellow. And we see that while their averages are pretty similar to each other, there is a much wider range in permutation feature importance across all the models generated by the humans versus those generated by the robots. It's a slightly more condensed, similar, unified product that the robot provides. And additionally, too, the robot uses a wider variety of V-near wavebands to generate its model than the human model does, which tends to rely, as we look at these little lollipops in there, on a few different features most heavily. So what that is due to, we're still digging into this data, and that's part of phase 2, which is then, now that we've established that we can use this robot to train remote sensing data, we're now looking to close the loop with the second half and use the remote sensing to target ground validation with the robot or with humans to the areas of greatest uncertainty, either regions of the model that need improvement or ones that are showing that are most likely to have disease occur. So as I mentioned, this project has been funded both by NASA as well as USDA NIFA, and our funding from NIFA has come in partnership with the VITUS Gen 3 SCRI project, which has been about improving, for the most part, grapevine breeding for disease resistance. So this season we deployed either the PPB or a camera and its model similar to it across 5 different locations across the United States: California, Minnesota, South Dakota, home in New York, as well as in West Virginia. And we now have all this different these data for these different breeding programs in these different geographies that have also been paired with remote sensing imagery, either from commercial sources or from space agency sources. Additionally, in field season 2024 and 2025, we've been looking forward to closing the loop even further at commercial vineyards. In 2024, led by my outstanding graduate student, Kaitlin, we conducted our first multi-sensor campaign at commercial sites that included UAV-based hyperspectral, multispectral, and thermal sensing, along with the PPB, the robot multispectral, as well as multiple handheld devices, as well as a molecular test for plant chemistry and disease, confirmation. So through funding from these different sources, we're addressing and continuing to close the loop across all different spectrums with this multimodal, multi-sensor, multi-scale idea. And as I mentioned before, this has really become the kind of central theorem that we've coalesced our projects and our collaboration around. And our 2 students, Leo Irtai and Kaitlin, have had such a wonderful partnership. We've now recently established Students 2.0. We have Nico and Yuan, who have recently joined both of our labs that will be working in this kind of space to both on their own innovation and research motivations within their domain, but also together to enhance both of their dissertations. Nico will be working to sense all 3 elements of the disease triangle to design responsive disease control programs on semi-resistant varieties, while Yiwan is attacking that 10% threshold problem, and he's developed some really innovative computer vision models that integrate in LLMs that can intake both text as well as visual cues in order to determine whether or not it's disease. So more of that human expert information can go into the model for when the robot says, is this diseased or not? And this has been really helpful in trying to break through that 10% threshold. Oh, and he's additionally, if you can see here, he's upgraded our robot. It's got a way better base now, which is really excellent because this one is also less likely to run people over. So just some final thoughts. So pathosystem biology must be foremost in your mind when you're designing disease sensing systems, whether they're for phenotyping or management intervention. And this is because disease is a dynamic process. It's the result of vibrant, exciting elements that are all kind of oscillating on their own timescales, whether it's the environment, the pathogen, or the host itself. So you need to keep this in mind, and keep in mind that you are sensing the pathosystem and not just simply any one element of the disease. And if you want to build dual-purpose solutions, you really need to consider that human element. What are the factors that stakeholders weigh when they're considering making a management intervention? Can you optimize your system to provide them with that? Not every disease needs hyperspectral as its sensing modality, depending on what will actually inform a reasonable decision that they can make. Simply knowing where to go scout could be just as useful information as telling a grower that they have an asymptomatic infection. So talking to them, working with your humans, understanding their decision-making process is key when you want to build these systems. And then also that phenotyping technologies can and should be adapted to be dual purpose. A rising tide lifts all ships. For example, our systems were built with the idea in mind that they would be eventually used across breeding programs across the United States. This has changed how they're engineered, how they're resilient. When you're building a robot that's supposed to go into commercial environments, you don't know what it's going to encounter. This makes for a more rugged, more supportive, a better adapted system for the long run. And additionally, too, I really believe that working with stakeholders is the most important thing that we can do. Understanding their challenges, their needs, and how we can optimize our systems to help them will benefit the direct science that we do, even if the exact thing we're working on is not something that they will ever likely have in their hands. So with that, I'm 1 minute and 32 seconds over time. So I'd like to acknowledge my lab members here, in particular the graduate students whose work was featured, Leo, Kaitlin Canali, and Fernando Romero Galban. And I'd also like to acknowledge my research partner, Yu Jiang, the closest thing one could have to a best friend in science. We've been working together for now nearly 5 years now. This project was conceptualized during the pandemic, and in the time since, we've grown our labs from 0 people to, I think, over 25 people total between the two of us. And we've respectively been growing our family. So there have been 3 children born during the time between. We started this project, and now we're continuing it. So with that, do I have time for questions, or is that it? Oh, I do. Okay, how wonderful. Yeah, thank you for having me here.
Thank you very much, Katie, for really bridging the plant biology, the sensing, the robotics, and the decision-making in this fantastic talk. We do have time for some quick questions now. There was also going to be opportunity later on in the session to ask more in-depth questions, and we do have roaming mics. There's a question here at the front.
I can hear you.
Really nice example of disease detection using remote sensing. Do you envision incorporating epidemiological or weather modeling?
Yes. Yes. Oh man, I'm kicking myself because I deleted that slide last night. Yeah, so absolutely. As we're thinking about phase 2, that's one of the things I'm most excited about is adding in the mathematical modeling, right? So both from the modeling side and I think the remote sensing side, we can really benefit each other. When I talk to modelers, they salivate at the idea of having a true map of where disease is to parameterize their models. And additionally, too, what I would really love is how I can take my imagery and leverage that really decades of work on how disease is spread to weigh my model classification. So I think we can both really benefit. As well as derive new information that's novel and not just simply operational. I have a postdoc who's coming in who's really excited about applying principles of game theory to understand how grower decision-making impacts epidemic progression using data from remote sensing as well as modeling. So we can take these things and use these 2 different domains to make better, science product engineering products, I guess, so phenomics, tools, systems, but we can also use them to derive new knowledge that advances both domains.
Fantastic. Yeah. We have time for another quick question. Oh, there's one over there.
Oh, thank you. This is very cool. I have a quick question about the resolution. And you mentioned that in your airborne remote sensing, the highest accuracy is using the 3-meter resolution. I just wonder why 3? Is that because the size of the plants or how the experiments were designed? And also relate to that is when was that accuracy achieved at what stage of the disease? Thank you.
Yeah, absolutely. So we found that in that AVIRIS work, between a comparison of the native 1 meter resolution, 3 meters, and 5 meter resolution, that 3 was the optimal for maximizing accuracy for all different sorts of combinations between symptomatic, asymptomatic, non-infected, asymptomatic, and more combinations thereof. So those are the 3 resolutions that we had because this is an aircraft, right? So your resolution is determined by how low the pilots are willing to fly. And they're really, modern cowboys. Like, they were willing to go pretty low. But the finer your spatial resolution, you also have to have very fine ground validation because you can also get a pixel that you might have like a bit of a miss in terms of what the human measurement of disease on that vine could be a little bit off. So it's really that signal to noise that we found that 3 meters was that optimal, that minimizes signal to noise and allowed us to kind of like dampen out the issues of soil. These are like bare ground, there's not a ton of vegetation that kind of look like this is the vine. It's a very, very thin layer, especially in California, of the foliage that's actually at the top. And the reason why we worked with 1 through 5 instead of going even higher was because that when we found that we started to bin it even higher, we were limited by the fact that we didn't have more extensive ground validation. Our stakeholder partners really came to support us. They scouted over 300 acres on a vine-by-vine basis. However, what we really needed and we couldn't have because it was 2020 pandemic era was ground-based spectral measurements that would allow us to do better unmixing. So that was the first half of your question, but I can't quite remember the second half. Started going off.
At what stage your highest accuracy?
Oh, what stage was the highest accuracy? Now, that's a really interesting question. So overall, everything was pretty comparable. Everything ranged, once we kind of hit that optimization, between 80 to 87%. But the best accuracy we had, that 87%, was actually distinguishing between non-infected and asymptomatic. And what was really interesting was that when we made a 3-part model to distinguish between non-infected, asymptomatic, and symptomatic, we actually found that model was getting confused it confused very frequently between symptomatic and asymptomatic, which was both bad because we want the model to be better, but also good because it meant we were sensing physiology, right? It makes a lot more biological sense that this model would be confusing asymptomatic and symptomatic because the underlying processes that are driving our ability to detect are consistent. But the best accuracy was between asymptomatic and non-infected.
Thank you. Now, there was one slide where you mentioned that the disease detection accuracy was coming close to the human expert, so the guy with the hat, forgot his name. And what I find interesting is to figure out how good he is actually able to repeat himself.
Mm-hmm.
And also between examiners, are they agreeing with each other as a ground truth judgment of your algorithm? Can you comment on this?
Yeah, okay, so the question is, so the slide I think you're referencing is my vineyard manager trained the model, the computer vision model, but how well can he replicate his own measurements, right? Is that the question?
Yeah, and does he agree with other experts?
Yeah, that's a great question. So we've not specifically tested how well he agrees with himself, though we could, he's annotated multiple images, and there have been instances where he'll say, I swear I looked at this before. So we could go back and do an assessment. We have a standardized training method for scouting that's based on Dave's method that we use to train everyone who does our scouting. One of the slides I mentioned that we do scout teams. So we've not specifically gone back and looked to see the correlation between the human scouts, but we could, given how we structure the scout teams, which is that 2 different people will go and measure each panel, and then we'll take the average measurement.
Yeah, so my point is that these tasks are then super seriously done because you are training your algorithm or the AI, but on a regular day, they are in a hurry, so they might they actually perform less than when they train your algorithm. So maybe your algorithm is actually already better than an average day on the job.
Yeah, no, I think that's the case. I mean, so like numerically, we see them perform pretty equivalently, but that's pretty much, I think, one of the main drivers behind robotic and automation, right? Is the robots don't complain. You know, graduate students have many fine qualities, but one of them is not working for unlimited hours without complaint. And, you know, you and I both would get exhausted by the end of the timing. There's a body of work in plant pathology showing that disease measurements get more and more variable as the time spent making them goes on. So that is an advantage of using the automated systems, is that they're consistent throughout. You don't have that degradation over time.
Yeah, but if we quantify that, then we get actually quite a good argument pro automation.
Yeah, exactly. It would be a good justification.
Yeah. Cool.
Thank you.
Any other questions?
Thank you. So you showed the robot. Do you think it would make sense to put these sensors on the general machinery that farmers use? And what would that mean for the remote sensing approach? Would it still be relevant? Because you, as you said, you measure the side of the canopy, which is perhaps more informative.
Yeah, that's a great question. So I think one of the cool things about the robot is, you know, it's of course a robot, but it's made of multiple components, right? Like it's a robot itself. It could be adapted for many different vineyard purposes. For example, we now have one of the next generation one has swarm technology, and it like follows behind with a little like bin for harvesting purposes. But the sensor on the side, right, like that, as you say, could be mounted on any sort of farm equipment. Especially given that vineyards have pretty regular activities that go on. So perhaps not during spring just because of like all the fungicides blowing around, but we certainly could mount the sensor and then use those models on tractors. And then in terms of the remote sensing, I see this as a very much a systems approach. And it's also given that growers are generally slow to adopt technology, and not everyone has the same production goals or like the same production finances where it would make sense for them to invest in new technology. But by using an integrated system, we can use the remote sensing to provide a better result for all members of the community that they don't necessarily need to have the ground technology to access, right? So if, you know, maybe 10% of growers in a region are using these sensors either on a robot or on the tractor, and we can use that to improve the remote sensing models and provide that for all growers within that region, you know, the whole community benefits, even though not everyone is like adopting the technology. So, you know, I think it's best to think about remote sensing, proximal sensing, and all the gradations thereof as they're not one, you know, it's like, let's not try to think of them as hammers and looks for nails, right? Like they all have their pros and cons, what they're good at, what they're not so good at, and thinking of that systems approach, right? Remote sensing doesn't have to be the be all end all, and the robot isn't the be all end all. It's about using a systems optimized approach. Thank you.
Here?
Yes. Hi.
You've highlighted the need for pre-symptomatic disease detection. I'm curious, how do we define spectral signatures to detect diseases at asymptomatic stages?
Yeah. So I do not believe in disease signatures, and I especially do not believe in pre-symptomatic disease signatures. And I know this might be a controversial take, as I did once previously believe in disease signatures, because disease, the one we're sensing once again the pathosystem. And it's the confluence of the pathogen, the environment, the host all together. So you're sensing the reaction, for the most part, of the plant to being infected. And that happens a little bit differently every time. Now, of course, there is commonality to these things. But as one of the talks earlier showed, like these, you know, same pathogen, different races, but are causing all these different phenotypes, right? And even ones that are causing the same phenotype, it's happening a little bit differently each time. So when you're sensing a pathosystem, you're sensing changes to physiology. I think if it were possible to develop a signature, and as we do for, you know, for exact nitrogen, or as I mentioned in question, a spectral feature associated with the phenolics ring, we would have had that already for disease. But that's just not how disease works. You know, if you're phenotyping for abiotic nitrogen stress, like there's spectral features that are directly associated with the way the triple bond, interacts with light. That's just not how disease works. So I do not believe in disease signatures. I don't think it's a fruitful venture to try to pursue them. And I think instead thinking about physiology, and you can look for, commonalities in physiology, right? And or you can just, take the machine learning approach, right? Like the spectra are different, and we do both. We both try to dig into the physiology and say, well, they're just different, and that works for me. So.
Right here, sir.
Yes, I have a question on the field. If you look at the different locations, quite often actually you see the same disease happening in a particular spot in the field, for instance. So since you have been recording these diseases over 25 years, did you notice some specific spots, and can that maybe be used as an indicator region for the rest of the field?
Yeah, absolutely. So, growers will be the first to tell you that when they're going to get powdery mildew, they're going to see it here first, in the low spot in the field, those sorts of things. So in a kind of unofficial sense, yes, we've been tracking. The utility of that sort of information, I think, one, depends on your goals, and then also two, gets to that concept of the action threshold, right? So if we know that if we're anticipating getting a disease every year, kind of like common flu style. So an example that I present today would be downy mildew, right? Then monitoring those spots in particular would be quite useful. Otherwise, if it's a quarantine disease, we don't necessarily know, right, where it's going to be, but we could guess based on if we're looking for something that might be expanding out of transport networks, or with spotted lanternfly, that sort of thing. So we can that's absolutely possible too. And I think that's, there's an earlier question about epidemiology and mathematical modeling. And those are the things that I think are kind of this next era of plant disease sensing, right, is integrating with modeling for strategic monitoring and deployment thereof.
Okay, now my turn to ask a question. Sorry, I've been busting to ask that one. Well, it's sort of following on from what you talked about earlier about there not being specific disease signatures. How good do you think we will be at differentiating between, that part is infected with downy mildew, that one has a viral problem, that one has botrytis or some other? How good are we going to get at differentiating the different pathosystems?
That's a great question and something I think about all the time. So my colleague, the one that gets all the Nature papers, I don't get those. My colleague Pablo Zarca-Tejada in Spain, they found that you can distinguish. Oh, yes, he's going back to Spain though. Yeah, I know. Where was I going? So they found that visually identical symptoms, one caused by wilt, one caused by abiotic stress, that they can distinguish those spectrally, right? They have different spectral pathways that correspond to the fact that they come about via different physiological pathways. So it is possible from that kind of fundamental sense, okay, even if the stress that is causing different sources is causing the same plant reaction, there's reason to believe that you can differentiate them. But in terms of how good are we going to get, that's hard, right? So if something is causing wilt, it will always look more similar to another wilting plant than it will to anything else. And that gets to the idea then of this contrasting disease physiology. I think that we have much more potential for more rapid success in distinguishing between diseases that have different physiology. For example, the viral disease, a systemic disruptor versus foliar necrosis, or a vascular disruption sort of thing. So if we can, instead of thinking of disease along the taxonomical categories that were so hammered into our head in Plant Path 101, we need to think more of the physiological categories. So it doesn't really matter if it's caused by a bacteria or an oomycete, but if it's disrupting the vasculature, it's going to be either probably harder, easier, we'll see, to distinguish from another vascular disruptor, probably easier to distinguish a vascular disruptor from foliar necrosis, etc.
Yeah. Any other questions? Oh, there's one over there.
I'm pleased to get these questions. I was worried oh no, the talk's gone, flown out. So I appreciate it.
No, thanks for the talk. I was triggered by this connection back to the grower. So how, once you're developing this and it's clear that it has its true value, how would you deliver this to the grower? Because also that grower needs to grow its trust in these types of systems and then take these actions. What would be your proposals there?
Yeah, so actually the reason I'm unfortunately leaving at 2 p.m. today is because I have to get back for a grower working session tomorrow exactly about translation. It's a hard question to answer, right? And it's also kind of brings up like, well, what is the role of an academic lab? It's, you know, to an extent, right? Like, is it our job to provide this service to all growers, or is it our job to make this capacity with their needs in mind, with them hand in hand, and then transition it to the private sector or some other sort of more kind of sustainable long-term system, right? Because I guess you think of an academic lab, like, you know, we're churning out innovation. So it's a hard thing. You know, my lab's coming up on its 5-year anniversary, and we're now kind of we've done those things. Like, we have those, like, okay, check. These are things people want. And now it's like, well, do we provide this to the growers ourselves, or do we try to work to transition this to the private sector or some other sort of like cooperative? It's exactly what I'm going through right now. And so I don't have like this is how it should be done. If anyone does have an idea on how it should be done, I would love to hear it. But we are, you know, investigating multiple options. But I do think that, you know, there's a couple different ways to ensure sustainability and use. And I do think partnering with the private sector is important. Also, too, you know, extension, right? Like, depending on these tools, we have a wonderful extension network at Cornell that's really well versed in like digital viticulture tools. So like training and offering those opportunities to adopt in that way. It's hard, though. I mean, I can keep blabbering on, but I don't know.